Hello and welcome, honor students. Today we are going to wrap up all of chapter 15. So we're going to go through 15.3 and talk about heterogeneous aqueous systems. And we're going to differentiate them and compare them to a solution. So we're going to talk about those particular terms. So the test that we're going to have next week on Thursday will actually be 15 and then chapter 16.1 and 16.2. So Friday we will have a virtual lesson on all of 16.1. So that you have to look forward to for Friday. So let's get started on this here. So we start off with a case file. We always do in all of these. And it says, why are some sunsets red? So think about this. This is actually because of an effect that takes place. The actual air with water droplets and dust particles are forming what's called a colloid, and we're going to talk about them a little bit later. And as the light goes through this, it is bent, and that is called a Tyndall Effect, and we're going to talk about that as well. So this actually is showing us two different concepts wrapped into one. The effect of these water droplets and dust particles being trapped in the air and not being pulled down by gravity is creating what's called a colloid. And the fact that the light is coming through and being diverted and causing these different colors to appear is called the Tyndall Effect. So two different concepts wrapped up in here. And we're going to talk about both of those. So first off, let's talk about a suspension. What is the difference between a suspension and a solution? So let's think about, first off, a solution. We've talked a little bit about solutions. It's been a while. It's been a couple of months. We talked about a solution being one phase. So if you took some salt and you have this container right here, and it has water in it, and you put some salt in it. You have a little container here, and you pour some salt into that. And you stir it. That salt's going to disappear. That becomes a solution. So that solution, the particles are very small, actually 1 nanometer or less. We'll talk about that a little bit more. So that becomes a solution. So when you look at it, it is one phase. You don't see distinct areas or parts. When you talk about a suspension is not a homogeneous mixture. A suspension is a heterogeneous mixture, which is said to be 2 or more phases. And we'll talk about that. So let's define it. A suspension is a mixture from which particles settle out upon standing. So think about this. If you took a jar, have some water in it, and you took this little container and you poured in some dirt. You mixed it all up, and the dirt is all throughout it. Now it's all cloudy and murky looking, and you set that down. You wait about an hour, you come back, and you're going to look, and on the bottom, you're going to see sediment deposited. That was because it was a suspension. And a suspension is a mixture from which particles settle out when it sits. This is a key term here, so please get this down into your notes. So suspension should be in your notes. So a suspension differs from a solution because the particles of a suspension are much larger. So remember, we said that a solution is very tiny particles, salt or sugar added into water. You know they're very small and they break down. So here are some key contrasts. So a suspension has a diameter greater than 1,000 nanometers. So remember what a nanometer is. So we have 1 times 10 to the negative 9 meters is a nanometer. So a nanometer, so if you have 1 meter, you have 10 to the 9 nanometers. So extremely tiny, very small. So when you talk about this, the average size of a suspension is about 1,000 nanometers. When you heard me just say this, when you talk about a solution, remember it's one phase, it's all dissolved throughout. A solution is typically about 1 nanometer. So very tiny, that's how it can become one phase. Where you have larger particles that create a suspension, they're much larger, 1,000 times larger actually. So it doesn't dissolve, so it actually will float in the water and then it'll settle to the bottom. So a solution is a homogeneous mixture. We learned that previously in another chapter. Suspensions are heterogeneous mixtures because at least 2 substances can be clearly identified. So 2 or more phases. That's a key term that we learned about heterogeneous mixtures. A homogeneous mixture is 1 phase. Heterogeneous is 2 or more distinct phases. That means when you look at it, you can see contrasting areas in it, particles floating, areas of, like, for example, layers, like oil and water, or sometimes layers can form in the middle. So those are called phases. So that's a identification of a heterogeneous mixture. So the difference between solution and suspension, if you pour a solution, and in this case here, right here you see this blue substance, that's more than likely is going to be copper sulfate. Pour it right through, notice on the bottom it's blue. You can't filter out a solution. The only way a solution is separated is by distillation or just allowing it to the water to evaporate. When you talk about a suspension, you can filter it. You can also do decanting. Remember pouring it off, or suction decant in the lab. I used to do that. Just you have a suction device and you let the sediment fall to the bottom and you suction off the top. So that is how, in fact, you can separate them. But the main way is filtration for heterogeneous mixtures. So, checkpoint. Explain why a mixture of sand and water can be separated by a filter and a mixture of salt and water cannot. We just talked about that. Hopefully you got this aspect. So you have larger particles. So it is a suspension when you talk about sand and water, and you can filter it because it can't dissolve in it. And when you talk about salt and water, that's a solution. It's one phase, so it's dissolved inside. All right, so colloid. So what is a colloid? And we're going to talk about the difference between a colloid and a suspension and a solution. You heard me mention colloid at the beginning of that case file with the dust and the water vapors in the sky. So let's talk about what a colloid is. So a colloid is a heterogeneous mixture, but the particles are in a range. They're between a suspension and a solution. A solution particles are 1 nanometer. Suspension's particle size is 1,000 nanometers. When you talk about a colloid, it's in between. And that's the part to remember, it's in between. So the particles are spread or dispersed throughout the medium, whether it's a solid, liquid, or gas. And what happens is they stay there. They're not going to settle to the bottom because they're not big enough to fall out. So they just kind of stay within the whether it's a liquid or a gas that they're a part of. They just hang out in there, so they're not going to fall to the bottom. So please make sure you get this. A colloid is a heterogeneous, another term for your notes, please. You have to be able to differentiate these. Colloid is a heterogeneous mixture containing particles that range in size from 1 to 1,000. So remember, you see 1,000 nanometers or more, that's going to be a suspension. You see about 1 nanometer, that's a solution. And then when you talk about a colloid, it's in between. So some common colloids that we all know about. So whipped cream, the gas is in the cream. It doesn't fall out, doesn't escape. It's just there. We talk about a marshmallow. It's a solid and it has gas in it, and it's spongy, you know, by the feel of the marshmallow. It doesn't escape. It stays in there, so that's a colloid. Liquid it's a colloid, but it has a different name called emulsion, and we'll talk about that a little bit. Milk and mayonnaise is an emulsion because it's both liquid state. If you shake it up, put it in milk and shake it up, you can see it floating, but it will never, you can set it on the counter, it's not gonna fall to the bottom, it's just gonna stay between and stay inside of that liquid. Here is what we talked about, dust in the air and water vapor. And that is important because that's why you get those effects of color in the sky. So colloids have particles smaller than those of a suspension, we talked about that, and larger than a solution. So this intermittent size cannot be retained by filter paper, so therefore you can't just filter it out. That's real important. And another thing is they do not settle out over time. So if you had this container here and you had this liquid and you had these particles that are inside that you can notice them there, sit it on the counter for a day, come back, it did not fall to the bottom. It's still suspended inside there. So that means it's a colloid. It is not a suspension. Because if it was a suspension, the particles would have been large enough and they would have fell to the bottom. I mentioned the Tyndall effect, so let's talk about a Tyndall effect. In class, I had plans. I was going to do this in a little activity. I might be assigning this as a bell work coming up here just so you can see this. It's kind of neat to look at. You cannot see a beam of light as it goes through a solution. So if you turn on the light and you have, say you have a container and you have salt and water in it and you shine the light through it, you don't see the distinct beam passing through there. So you cannot see a beam of sunlight unless the light passes through particles. That's the key, to scatter it. So these particles scatter the light. So similarly, a beam of light is visible as it passes through a colloid. You don't see anything when you pass a light through a solution of really any type of solution that you might make. So here's the Tyndall effect, and this is a term, so please get this term down into your notes. The scattering of visible light by colloidal particles is called the Tyndall effect, and that's what you see in the sky when you see all those colors. It's a colloid in the sky because those particles and the water vapors are not falling out, and the light passing through gives those colors that you see. So let's look at this right here. So I mentioned a solution. So remember, a solution is salt and water, sugar and water. You could put copper sulfate in water. So there's various things that you could do. You could add milk in the water and shake it up and you've got yourself a solution. So, but when you look at passing a light beam through it, notice under solution, you don't see the light. You don't see the actual distinct beam. When you pass it through a colloid, you now see it specifically. You see the light beam going through there. When I said milk and water, that actually I should have mentioned that as colloid, because those particles are going to disperse and they're going to just stay mixed throughout it. So that wasn't a good solution example, and that you would be able to see this beam of light. So a colloid, the particles don't settle out and you'd be able to see distinctly that. And in a suspension, so if you had some water and you put some dirt in and you shook it up and then you held it and then all the particles through there, you shine the light, you would be able to see the beam of light passing through that. Why? Because those particles are moving and causing the light to bounce off of them and it would be redirected. So that is the Tyndall effect. And please know this is important to know this effect. Solution, you don't see the light. Colloids and suspensions, you can. So suspensions also exhibit the Tyndall effect. The particles in a solution are too small to scatter the light. Brownian motion. So let's talk about Brownian motion, what that is. Flashes of light or scintillation are seen when colloids are studied under a microscope. So colloids scintillate because the particles reflect and scatter the light, move, and it's erratic. So think about this. If you had a little pack of yeast and you have a cup of water and you drop a little bit of the yeast into that cup of water, the cup is still, it's not moving, it's on a counter, the water's not moving. As you drop them in there, you're going to start to see those yeast particles move. Why is it moving? The water's not moving. That's Brownian motion, actually. So it's moving because the molecules in the water have kinetic energy. We talked about that. So they're in constant motion. So it's actually striking and moving and scattering those little yeast particles that you dropped into the water, and that is why. And that's a form of Brownian motion. So colloids scintillate because the particles are reflecting and scattering the light, move erratically. So it was discovered by a scientist, actually a botanist who works with plants, Robert Brown, called Brownian motion. I'm not interested in you knowing the dates or who invented it. Just understand the chaotic movement of colloidal particles is Brownian motion. So Brownian motion is caused by collisions of the molecules of the dispersion medium with the small dispersed particles, the colloid particles. So similarly, like I said, the water molecules striking it are causing it to move, and that's called Brownian motion. And that's why it doesn't settle. It can't settle because they're constantly being hit. That's another really important note right there. The reason they don't settle out is because it's in constant motion, so it's going to stay striking molecules and stay moving. Coagulation. So we've heard of this term before. Let's talk about a little bit on that. So colloidal particles also tend to stay suspended because there's charges involved. If it's in with ions, you can get some charges on the surface, and it will keep them apart and also keep them moving around. So that is a kind of something that you need to be aware of. All the colloidal particles in a particular colloidal system will have the same charge, although the colloidal system is neutral. And why they get these charges is repulsion between like charges, particles preventing from forming heavier coagulates. So that's why it doesn't fall to the bottom. They do pick up these slight charges just because of the constant striking and the motion that is going on in the system, and it's going to repel each other. So not only are they being struck by molecular movement, but there's also some repulsion between those colloidal particles, and that also keeps them apart. So important. So, but you can destroy a colloid system. How can you destroy a colloid system? By adding electrolytes. And remember what electrolytes are. We talked about them in the earlier section. Electrolytes carry a current. So if you have something that carries a current, now you're forfeiting the charges that they had because now you can move other charges through them. So adding ions, so if you added salt or you added something into it, some form of a salt, sodium chloride or calcium chloride or potassium chloride, something of that nature, it will actually cause it to neutralize the charges, because now you have, remember, when you have a salt added, you have positive and negatives. Now you've neutralized it because it's going to cause an attraction to the opposite. And what it does is it causes them to clump together. So it forms these clumps of charge, these charge attractions now, negative and positive, will clump it together and it will cause it to settle out. So it causes to form these heavier aggregates, and that is what is coagulation. Coagulation is clumping together. That's what that term means. So let's talk about emulsion. An emulsion is a colloidal dispersion of a liquid in a liquid. Emulsion is a liquid in a liquid. So that's another vocab term. Please write that down. So when you talk about colloids, if you are specifically talking about a liquid and a liquid, that's called an emulsion. So an emulsifying agent is essential for the formation of an emulsion, and to maintain stability. So let's talk about that a little bit. So oil and grease are not soluble. We know that. But if you add a detergent or some soaps, that's how they work. They are emulsifying agents. So you add into some of this oil, you have some soaps or detergent. Part of it is polar and the other part of it is nonpolar. So remember, oils and greases are nonpolar. So when you have these molecule chains of soaps and detergents, one side is typically nonpolar and the other side is polar. So how does that work? This part here dissolves the nonpolar, like dissolves like. And because it's now dissolved within it and this side is polar, it allows it to immerse into the solution that you're talking about. So one end of the large soap is polar and is attracted to the water. The other end is nonpolar and soluble in the oil. So soaps and other emulsifying agents allow the formation of colloidal dispersions between liquids that do not ordinarily mix. So if you had grease, you try to put it in water, you know it's going to form a layer. Two distinct phases will happen. However, if you add an emulsifying agent like soap, now it will actually form a colloid system inside there because it emulsified it. So important to understand that concept. So here is a nice little scale. It has a solution, colloid, and suspension. This is the key note right here. Very important to understand that. And then we talked about the size, about 1 nanometer or less for a solution. A colloid is between 1 and 1,000 nanometers, and a suspension is 1,000 nanometers or larger. So when you talk about Tyndall effect, solutions have none, but colloids and suspensions have a Tyndall effect. Filtration, you can filter a suspension, but you cannot filter a solution or a colloid. Remember, they're too small, they actually go through the filter. And these are both called heterogeneous because you can distinctly see 2 or more phases. And then in a homogeneous, which is a solution, it is said to be 1 phase. So, last checkpoint of this section. Which of the following is a colloidal system? So remember, a colloid doesn't fall out. So, mud. If you took mud and you have water with dirt in it, it's mud. If you sit it down on the counter, what's going to happen? It's going to fall out. Gasoline. Gasoline is actually a solution. It's a homogeneous. It's 1 phase, so that's not it either. A mixture of sugar and water. Well, no, that's a solution as well. So that leaves 1. So your answer should be a colloidal system is blood. Now, you may be thinking, wait a minute. They can separate blood. That's with a centrifuge machine. So remember how that centrifuge machine actually works. You have to put 2 test tubes, 1 on each side for balance purposes, and it spins it. So by it spinning it super fast, it is going to make those colloid particles, centrifugal force is going to make it go to the bottom. So that's not a normal means. That's in a machine that makes it fall out. But a colloid system means the blood, red blood cells are actually going to stay suspended in the blood plasma. So ladies and gentlemen, that is it on 15.3. So we talked about suspensions, colloids, we talked about the Tyndall effect, we talked about the sky and the different colorations being a Tyndall effect. We talked about Brownian motion, the random motion of particles striking these colloid particles and making them move. That's Brownian motion. We talked about emulsion, and that is the end of 15.3. So thank you for watching this virtual lesson, and I will have the next one out for you on Friday. Go in peace. Thank you.